Hi, this is Rohan from 1301, and today we're going to be going over two searching algorithms, linear and binary search. We're going to start by going over linear search because it is the easier of the two and the more intuitive one. Linear search is also known as sequential search because it essentially checks each element one by one. Given a list, a linear search algorithm will traverse through each element and compare it to the element you're trying to find. If it finds a match, it will return the index of where the element is in the list. Otherwise, it will keep traversing through the array. Let's start with an example. Let's say we have the array with the elements 2, 6, 9, 3, 5, 6, 7, 8. So the linear search algorithm will start at the first element in the array and compare it to the element you're trying to find. Let's say we're trying to find the element 5. So it'll start at the beginning of the array and say, is the first element equal to the element you're trying to find? So since 2 is not equal to 5, it's going to go to the next element. Since 6 is not equal to 5, it's going to go to the next, and eventually it'll reach the 4th index in the array where we have the element 5 stored. So since this is equal to the element we're trying to find, this linear search algorithm will just return out 4 for the index where the element is stored. If it wasn't located here, it would keep going throughout the rest of the array. Another thing we can talk about with this search algorithm is the time complexity. So the best case time complexity for linear search is O of 1. This is the case where the first element you're looking at is indeed the element you're trying to find. So say instead of looking for element 5, we're looking for an element with the value of 2. And if that was the case, then it would only take us one instance of looking into the array for us to find that the first element is equal to that. The worst case time complexity for linear search is O of n. This is the case where we have to traverse through the entire array before we find the element we're looking for. So say we're looking for the element with the value of 8, we'd have to go through the entire array before that. The average case time complexity is O of n over 2. Okay, next we'll go over binary search. So binary search is a little bit of a more useful search algorithm because its time complexity is better. The only requirement that binary search has is that the array must be sorted. If the array isn't sorted, then the searching algorithm won't work properly and might give you the wrong result. So once again, we'll start with an example. Let's say we have the sorted array with the values 1, 2, 4, 7, 9, 10, 14, 15, 19, and 20. Oops. Okay. And we can say the element we're looking for is 19. I'll also just write the indices of the array above it. So this algorithm works by repeatedly dividing the sorted array in half. So the first thing you're going to do before you can divide it in half is find your midpoint. So the midpoint can be found with this formula. It's the lowest index plus the highest index divided by 2. So in this case, we have the index 0, the index 9. So we'll add those two together and divide by 2. We get 4.5. But since we're working with indices, we're going to have to truncate the decimal, and we'll just be left with the index 4. And this is going to be our midpoint right here. So once we find our midpoint, we just say, is the midpoint value of 9, greater than or less than the element we're trying to find. So since it's less than, we know that the element 19 can only be on the right side of this array. So we can throw away this whole left side. Once we do that, we can bring that new array down. And we can keep those same indices above them. And we'll just once again find our midpoint. So that's going to be 5 plus 9 over 2. That's going to be 7. So our midpoint is at index 7, and that's going to be a value of 15. So since 15 is still less than 19, we're going to throw away this whole left side again and only use this right side and bring that down now. So we have 19 and 20 with the indices 8 and 9 above it. Once again, our midpoint is going to be calculated as 8 plus 9 is 17. 17 over 2 is 8.5. And 8.5 with the truncated decimal is just going to be left with 8. So now our midpoint is at the value of 19. And since 19 is actually the element that we're actually trying to find up here, we can just stop the algorithm and return maybe true if that's what our implementation was to say that the element exists in the array, or we could return the index that it exists at. It just depends on the implementation. So another thing to go over with this binary search is the time complexity. So the best case time complexity for binary search is O of 1. So that would be the case where the first midpoint that we find is the element we're actually trying to find. So say we're looking for an element with the value of 9. Since our midpoint is a 9 exactly, we wouldn't even have to throw away half the array or go to the next array or anything. We would just know that, okay, the element exists in the array. The worst case time complexity is O of log n. So unlike linear search where you have to traverse through the entire array, each iteration you're throwing away half the array. So after this first iteration we're only left with half, and then after the next we're left with another half. So that makes the worst case time complexity O of log n instead of being O of n. The average case is also O of log n. That's what makes binary search so useful, because even though you're searching for an element in an array, you can throw away half of it after each iteration. The only requirement is that the array must be sorted for it to work properly. All right, thank you for watching.